In this talk, we will talk about the threats that you have online every day, how attackers are brute forcing wherever they can, and of course we all dream of hacking back, of finding them, of finding a way to de-anonymize the attackers and put them down. Because usually you can increase your security, but that doesn't help everyone else. So how to track them down when, as we all know, hackers wear black hoodies? How can you find them? That's not very easy. So our next talk, our next presenter will introduce us to this topic. Please, big applause to Lars.
Have fun.
Hello and welcome, everybody. Thanks for taking the time to look at this talk. I want to talk a bit about attack mining. The whole concept and the whole idea of this whole talk and everything that I worked on this was to sort of work with the CCC ethos, that we actually do something, that we not only watch and listen, but actually we take care and really make sure we use the community to protect others that might be a little bit less vulnerable or a little bit more vulnerable than us in the way that we can detect stuff. Now, just quickly to myself, I'm Lars. In my day job, I am leading a detection response team for a major insurance company, and in my free time, I do projects like this. Now, how did this project start? It started with an auth log on Linux. So I'm sure some of you here have their own Linux system, maybe have their own server on the internet. Now, if you look at this Linux log, this auth log that I pulled yesterday, this is about 30 seconds happening there. And in that time, you can see not only one, but 10 attempts of somebody on the internet trying to log into my system. Now, this is in January where this whole story started, about a year back when I did an incident response on a case that we had, logged into one of these Linux, or a Linux system connected to the internet, and saw that there are so many attempts trying to log into the infrastructure that I'm protecting. And I was a little bit offended by that, personally. And I wanted to do something, not only to stop and protect my infrastructure, but actually to go one step further. Resulting out of this, I had a bit of a concept. Concept was, I have my adversary on one side and my system on the other side. Now, on my system, the adversary attacks my system, so tries to log in with root and password 123. Now, on my system, I do a bit of a trick. I actually replace the OpenSSH setup that every Linux system usually has on port 22 that you can see here with something that I call an attack pod. Attack pod is a Docker container designed to look exactly like a Linux system itself, but a little bit modified. And we'll go into this a little bit later. This attack pod then collects the timestamp, the source IP, the username, and the password that adversary tried to attack us into a centralized database, and eventually denies the request. So the adversary itself thinks they tried to log in to a system, and they just failed. They just got the wrong credentials. Now, with this concept, it also allows scaling. So I can have one more, or two more, or maybe hundreds of more systems out there that do the same thing, collecting attacks into one central location. Now, how do I build this attack pod? In general, there are three ways of doing this. There's the first one using honeypots. I'm sure everybody in here has heard about honeypots. They're usually designed to track the actions that the adversary does once they logged onto a system. They have a bit of a downside. They usually are very resource intensive, and they take a long time to set up. So that wasn't really what I wanted to do. I wanted to scale this up to a really, really big amount, and I don't have crazy amounts of money. So I sort of had to find something a little bit sleeker. Then there's another option, and this is what I call target emulation. Idea here is that you take the OpenSSH server itself, and you sort of re-implement the way that it works in a different programming language. That way, a login can never happen because that's not implemented at all, and you can still collect all the information that you wanted to have. In this case, what I want to collect is IP that tried it, username, and password. Now, I did do this about a few years back in Python, and it was a lot of work. Also, you never get it to the point where the adversary cannot detect it, because you always do something a little bit different than the actual OpenSSH server does. So to get it as close as possible to the real setup takes a lot of effort. Also something that I can't really do beside my day job. And so the only option left is to actually build a modified target. Now the idea here is that we actually take the OpenSSH server itself, and it's open because it's open source, so I can see all the code in it. I patch the OpenSSH itself to not only give me some logs back, but actually give me all the information back that I want, and also patch in the way that no logins are possible. The cool thing with this is, it's kind of a low amount of maintenance, because I can really easily set this up, and it's super stealthy, because it's exactly the same thing that every other, or pretty much every other Linux system out there uses. So for an adversary, nearly impossible to find this. Now, how does this look in detail? What you can see here is, if you download the OpenSSH source code, you can find a file in there that's the auth passwd file. And this file is a function. Function auth password. Well, I guess everybody in this room can guess what this function does. It is the function that is called every time you try to log into your OpenSSH server with username and password. Now, if you take this and modify it slightly, and the easiest option, that was 100% exactly the code that I used for the first attempt, is you just add a logit. Well, logit does exactly the thing that it says it does, it logs the line. So in here, usually OpenSSH only logs the source IP and the user, but I also want the password, right? So I adjust the logit to log the username, password, and the IP. Now, that's only halfway there, because I now have the log itself, but let's assume the adversary guesses my password. Then they can log onto my pod. And I really have to avoid that, because then they can attack my system. So I also add a return 0. What return 0 does is basically return false, so no matter which password is provided, it automatically returns false. And that way, nobody is able to log into the system. Now, once you compile this and put a little bit of script here and there around it, you get output like that. And if we focus on one line, I get exactly the information that I wanted to have. I get the username, I get the password, and I get the source IP. Now with this, I already have my first building block to actually do attack mining. Now, the only thing I need to do is to scale it up to about 250 sensors. So by today, this whole environment, this whole setup has 250 sensors in 25 different countries, which actually record 12.5 million attacks every single day. Put it into one setup. Now, having the network is sort of only halfway there, right? Now, I collect 12.5 million. This is actually gigabytes and gigabytes of attacks. I need to do something with it. So let's jump in and try to find the adversary. Now, in here, the first thing you can do is you map it on a graph. Well, basically everybody's attacking everybody. And you can see a really big red blob. Now, looking at this graph, it has some very crazy similarities with this graph. Anybody has seen this graph before? This is actually the graph of the amount of internet-connected devices. So basically, wherever there's a device connected to the internet, it will try to attack you. Which is sort of kind of a fun thing to see, but also doesn't really help me to find my adversary. I want to find adversaries and actually take them down. Now, that doesn't really help me. So if we can't find something with the IPs that we collect, let's look at the next fact. Let's look at the users. So from the users, these are the top users that were used to attack the sensor network. Starting with root, around 75% of all users tried are root. Then admin, Ubuntu, test, and so on. So what can we learn from this? Well, firstly, the adversaries try system administrative account. Well, why wouldn't you? If you're an adversary, you want to log in as admin straight away. You don't have to find some pesky privilege escalation stuff if you just can log in as admin. That's everything root, admin, and so on. Now, the other thing that I found interesting is actually that K0NIG user. The K0NIG is König in German, which is my surname, and that's also my domain that I own. So not only do the adversaries try admin accounts, they also do target-specific customization of the users they use. So the idea is that they look at the domains they try to target, and then they use the domains as usernames. And not rarely, they actually use that massively. Now, that username is in the top list because the first sensor, which is running for a while now, was on my own server, and so it got into the top 10 list. But digging deeper, you can actually see a lot of correlation between the domains that these sensors are sitting behind and the usernames being used. So that's a common practice around adversaries, to really try the usernames, or try the domains as usernames. Now, the third thing are default application accounts. Everything Postgres, FTP user Oracle, and so on are user accounts that are usually generated on Linux system once you install something. By itself, it's very, very useful and really good that applications run under different user accounts for security, because that makes sure that you have the right permissions for the right apps and so on. But that's also what adversaries try to target. Because if you install an FTP server, that user gets created. You usually forget it. Then maybe you do some debugging on it and give that FTP user just for the next 5 minutes, I give a test as a password. What can possibly go wrong? And it does go wrong. And that's exactly why they use it. Now, in itself, interesting data, but still doesn't help me to find my adversary. So let's look at the third part. The one part that is a little bit more interesting, which are the passwords. Oh, sorry. Well, what do we learn from this? Do not use root to log into your servers. Super important. I think number one rule, everybody tries to log in as root, and so you also shouldn't log in as root. Now to the password, to the fun part. Like, what? The top passwords being used by adversaries are 1, 2, 3, 4, 5, 6, and 1, 2, 3? And even my favorite one, the password 1. Like, seriously, if you use the password 1, you just, may not use the password at all. That's just, anyway. The sad thing about this is these adversaries, they earn their living by attacking. Meaning that these passwords must work. They wouldn't try them if they wouldn't work. So there are people out there that use 1 as their passwords and are probably not too scarce because it's the 10th most used passwords out there. But anyway, what do we learn from this data itself? First thing, there's a very large spread of passwords. If we look at the most used passwords, 1, 2, 3, 4, 5, 6, 3.6%. The 10th most used password, my favorite one, is only 0.3%. And from there, it gets smaller and smaller. Meaning that compared to the users, where there is a very static set of users being used, there is a huge amount of passwords being used out there. The second thing is the victim customization that we saw with the users. Basically doesn't happen. I found that super interesting because if I would be an adversary, I would absolutely also use the victim customization in the passwords because if I'm Lars, I might use Lars as a password because I will remember my name, I guess. So that doesn't happen too often. Now the cool thing is combining these two things, we can do something pretty neat, and that is adversarial fingerprinting. Now because of the fact that adversaries have their own little set of passwords that they use, they will reuse them. Meaning that if I can find a magic way to combine the username and password and then look across my whole environment or my whole data set, I might be able to actually identify which IPs are owned by the same adversary. And that's pretty much exactly what I did. So you take the three variables that we get out of the attack pods, which is the source IP, the username, and the password. First thing, you filter out common username and passwords. Main thing here is compute resources. I don't have infinite compute resources with 12.5 million attacks a day. There are a lot of passwords. So I just filter out all the root admin, all that stuff, because it's not specific to my adversaries. I also then combine the username and password together. Next thing is I do feature extraction and vectorization. And that's a little bit more complex. So how this works is every username and password combination is one dimension in a highly multi-dimensional environment. and I group together all the IPs and these usernames and passwords, and then draw the IPs in that thousands, million dimensional environment. Now, in the graph over here, I made it three-dimensional because that's easy for us to sort of imagine. Each one of the dimensions itself would be one combination of username and password, with each dot being one IP address. Now, the more often this username and password is being used, you move the variable or the IP within that environment. So once we've put that up, we then clusterize it. Now that's pretty simple. These are all standard algorithms being used for a lot of other stuff as well, but I can see which IPs are close to each other in that thousands and thousands dimensional space. And once I do this, I just crunch all these thousands of dimensional down into two, because we humans are really bad at imagining thousands of dimensions. So how does this look in real life? I took a data set of about 30 days, which is 450 million attacks overall. I then removed all the common combinations, as shown, which brought it down to 320 million. Already pretty good, but still a lot. And then clustered this. Out of this, I got 530 distinct clusters. Now, I have to say they're usually 531 clusters because there's one cluster, which is like the -1 cluster, where there are IPs that are so different that I can't really put them somewhere. But 530 clusters where I'm pretty sure that these IPs are using the same user and password combinations to attack the sensor network. Now, if you draw it up in 2D, I was hoping for something super nice and easy to view. Well, not so nice and easy to view, but I think if you use all of your imagination at whatever, 11:30, you will see some clusters here. You will see some groups. So there is for sure grouping. And actually, if you look into the data, that grouping is pretty cool. So what do I have now? I have a pretty good data set where I can see IPs, and I can group these IPs to adversaries. I can say that this group of IPs is very likely owned by the same adversarial group, which will allow me to dig deeper into it and to find out more about it. And I can do that on scale. Now, I guess let's look into one of these groups. So I went through them and found one group that I found particularly interesting. This is a group of 230 unique IP addresses that attacked the sensor network between February and December. Each of these IPs was only attacking for a very few days. Now, you might remember the really big red blob over China. Well, that was an adversarial IP that continuously attacked all of the sensors over months and months. With this, it's very different. This is only very sharp. Only a few minutes from each adversarial IP, my sensors were actually attacked. Now, the other interesting thing was that each IP scanned exactly 196 different combinations. Now, if you look at the graph below, that's a histogram of the amount of attacks that the sensor network saw. You can see this very distinct line in the middle where these are very, very similar to each other. Now, that caught my eye because I thought that's a pretty strong clustering. Now, first thing, same again, let's look at the three variables we have. Look at the IP and the geo mapping of the IP. It's, again, everywhere. It's not like I can say this is a network that sits in a specific region. Now, it's very hard to see here, but actually South Korea over on the right side there has a lot of dots. Now, obviously the dots overlay each other, so you don't really see it, but there is a little bit of clustering there, but nothing really crazy. So this must be an adversary that sort of attacks whatever it finds. Now, let's look a little bit deeper into these IPs. So I took them and ran them through Shodan and found out that most of the IPs are owned by residential ISPs. So the ISPs all of you guys use at home to actually access the internet. And only very few of them were owned by web hosters. From this, I can sort of assume that it's attacking IoT devices because, not many people have their whole server set up at home. To confirm this further, I also did some OS fingerprinting. Shodan mostly does that for you, but with digging a little bit deeper into it, I can see a lot of Raspberries, so Raspberry Pis, a lot of ASUS WRT, these are routers, as well as Linux as a general setup. Linux setup from home ISPs are usually routers or some other IoT devices that you have plugged at home. So with this, I can pretty much confirm that this adversary is attacking embedded systems. Now, from the IP, we don't really get further. Now, we know, yes, it's global, yes, it's a lot of sensors, they use X amount of attacks, but I don't really get anything further from here. Let's look at the next part, the username and passwords. Now, these are all the username and passwords used, and every single one of these adversarial IPs used exactly the same username and password combinations. Now, what interesting thing do we notice here? Firstly, usuario and contador. I'm really sorry, I don't speak Spanish, but these are two Spanish words for user and contractor. So it seems like the adversary sort of is targeting Spanish systems. Now, why can we make that assumption? With 169 different combinations, I guess every single one of these is sort of very well picked. So if two of the users and two of the passwords being used are exactly these words, they are likely successful with what it is. Now, if they attack a setup where they're successful, I guess it has to be in some Spanish-speaking region. Secondly, we can see some usernames being used that are application-specific. Now, these two I've never heard of before, so I Googled them, but these are sort of, one is an application or a database, and the other one is something similar there. So the adversary is targeting specific applications in a specific region. But overall, from the user side, nothing more interesting. From the password side, same thing. We can see all our favorite passwords, including one. That's also in there, so again, must be a successful password. But then there are three passwords that sort of stand out. I'm sure most of you have already spotted them. These three. Now, with 169 different tries, why would an adversary use a password that is 17 digits long and random? That's why. They just wouldn't do that. And so, because the fact that they randomly would guess the right password just doesn't make sense at all. So, the first thing I did, I used Google. And you might have noticed there's 33C3 in there. Well, I replaced the passwords with a new random password, but they're exactly the same length and type of before. And you will figure out why in a minute. Googling them, turns out other people have seen them too. But everybody says they have no idea why. Like, top 10 passwords are those, and just below is this random super long passwords, we have no idea why. Google the second one, same thing. Google the third one, nothing. That absolutely triggered my spidey sense to say, I need to dig into this further. Somebody in this community has seen this, doesn't know about it, let's find a little knowledge nugget, let's figure out what these passwords are. Now, with the data that I collect on the sensor network, I'm sort of stuck. I don't really have much more that I can see here. So I needed to get some more information. As my day job is incident response on endpoints, I sort of had to get hold of one of the endpoints to use what I can do best. So I searched through the list and found this endpoint. This endpoint was a Raspberry Pi Compute Model 3 in South Korea that was completely connected to the internet. Like, don't do this, people. Like, don't connect a Raspberry Pi to the internet, but they did. Now, I can see that this endpoint attacked the sensor network 3 times over the course of the year. And the good thing with this one was that on the same system, the owner was also hosting an Apache with the website. And on the website was a contact. So, after a few emails back and forth, telling, hey, I'm a security researcher, your system is infected, please don't shut it off, I want to know about it, they agreed to actually give me access. And a few days later, I had access to the Pi over the internet in South Korea. That was pretty cool. Now that was, South Korea and Germany has a lot of time zones, so, sort of in the middle of the night, I got access, and there was no sleep that night. So first thing I had to do is, I know the system is infected, and I know it's infected with an SSH brute force, because that's what I've seen. So I need to check, is it still infected? To do that, natstat-apn is your friend. That's a Linux command for everybody who doesn't know it that shows you all the network connections that are currently open. And voila. I can see that this setup, the system, is still trying to connect to a lot of random IPs on the SSH port. So I assume it's still infected, helping me or figuring out that, yes, this is a target I want to investigate further because I can find the adversary on that target. Now, jumping further, I had to find the process. Now, usually you can figure out from the socket that's open which process opens it and so on, but you can also do the lazy part and do ps3-a that shows you all the processes running on the system. Now, usually on a Raspberry Pi, and I'm sure most of you have one or have seen one before, there are only very few processes. That setup is not designed to run thousands of processes running parallel, so there are only like, whatever, 20, 30, something like this. In here, there were hundreds. And hundreds of APC ID. I had no idea what APC ID is. So jumped into Google again, figured out there should only be like one APC ID, maybe two, but max that. There were hundreds of those. So that's definitely suspicious. Let's look into this process further. To do that, on Linux there is a PID, process ID, that's 8621, that I can copy and dig further into net. So run the command ps-p8621, giving me more details about this process. And these more details include, for example, the user that started it. Now the user was root. That's interesting because I logged in as Pi after a lot of debugging, and the adversary seems to already have root privileges because otherwise they couldn't have run it. That's already cool. Now, the other good thing on Linux is it sort of logs quite a lot of stuff. Well, at least some stuff, including something called the bash history. Every time you run a command and you exit your terminal, everything that you ran in that terminal is written to the bash history. And part of this are these commands. Now what's a little bit weird here is, usually if you log into your Pi, you log in as the user Pi. And if you need to do something with higher privileges, you then move to the root user. Looking at the last three commands here, it's the other way around. It seems like somebody logged in as root and then moved to the Pi user. That's not typical behavior. Checking with the owner of the Pi, that's definitely not the owner did that. So yes, I'm onto something here. There seems to be an adversary out there. Now the problem with the bash history is you get the commands, but you don't get the time. Now I sort of have to figure out when did the adversary do that. And one way, not super reliable, so don't do this in IR, but it works, is to look at stat. Stat gives you the metadata of the file. Can be modified, I know, but it gives you a hint of when something could have happened. And somebody logged in as root on the system on the 20th. Now, what else can we see from the process itself? We can also see that the process was spawned on the 17th. So there must be regular logins into that system, giving us another hint where we might be looking. And finally, it also gives us the command. The command is exactly the binary that has started with that process, showing me where that binary sits, so I can look it up again, and again, I find a date on when that binary was written. And weirdly enough, the binary was written on the 17th, the process was started on the 17th, and some login into the root was or some commands were run on the 20th. So I sort of need to figure out what happened on these two dates. And that's very typical incident response work. Like we use these points to pivot from one point to another to make our life a little bit easier in searching through logs. Speaking of searching through logs, to run a command, you need to log in. To log in, you will leave your trace in the auth log. Going back to the auth log, voila, after a bit of searching, I find a login. I find a login from this IP with username and password. Again, checking with the owner of the Pi, definitely not an IP from the user. So yes, somebody out there logged into this poor little Pi in South Korea with a username and password. After the login, they did some privilege escalation. I quoted it here because you are already in the sudo group, so you can immediately jump to root, as well as they add a public key. Now, what's a public key? I think many of you might know, but it's sort of adding a second key to the system. You have two different ways of logging into a Linux system, or multiple different ways, but one way is username and password, the other way is private and public key. And they added this key, allowing the adversary to log back into the system itself by owning the private key. And a few seconds later, they logged out again. All that we can see here happened within 5 seconds. That's definitely nothing that you can type or I can type manually, so this very much looks like automated work. After the login, around about 5 seconds later, I can see another login using exactly that added SSH key. Meaning that what happened here is that somebody logged in as username and password, added a second key to log into that device, and then 5 seconds later logged into the device itself. Let's look at these different IPs. VirusTotal, your best friend here, it's super hard to see, but they're both known to be malicious. Now what immediately jumped into my eye here is this. Both of them have the flag Tor. The flag Tor on VirusTotal is set every time this IP is known to be a Tor exit node. Now that doesn't really make sense. We have seen that our infected Pi actually directly reaches out to victims and tries to log in there. It doesn't use the Tor network. So that doesn't really fit together. Maybe I've missed something. Go back to the auth log, this time using zgrab to also look at all the archives. And yes, not only did a big chunk of logs were missing, but I can also see other logins before the 17th, this case on the 15th, from a different IP, again with username and passwords. I can not only see one login, I can see a whole number of different logins. Looking at the IPs, they are all residential IPs. Again, IPs from ISPs, probably from other infected devices. And only a day and a half later, I can see a login from a Tor exit node. Meaning that this setup, this adversary, or this Pi itself, was infected by other, probably compromised systems from the same network, connecting to it, using username and password combination, logging in, adding that backdoor key, and then eventually, sometime later, in this case, day and a half here, probably the adversary itself used the Tor network to hide and then log into the Pi to do some malicious activity here. Now, if we look at some of these IPs, this is the interface that I built to monitor all the sensors and the attacks. I can see the same username and password combinations being used from these IPs against my sensors as well. Meaning that, yes, the IPs that attacked my poor little Pi also were part of that adversarial network. Now that we figured that one out, we still haven't looked at the malware itself, right? Now let's have a look at this one. The first thing you do in incident response, you take a hash. You don't want to show the adversary that you caught them. So you take a hash and put the hash into VirusTotal, or put it into Google. Again, no matches found. Now, this is on one hand cool, because I'm onto something new here. On the other hand, it's a real bummer, because I need to do the analysis myself. Quite often, it's quite nice that other people in this wonderful community do this analysis, publish about it, and I can just use their knowledge. Now, in this case, I got some friends from the community itself to help me with this ARM binary, because that's something that I don't do every single day. Now, I'm not going to go through every single step and the reversing here, because I will run out of time really quickly then, but I still want to show you how the whole infrastructure itself worked. So we have one infected device. This device has this APC ID malware on it. Now, the device uses a library to catch all the traffic that is going in and out of the network ports or the network devices of that individual device. So it checks which other systems are connecting to my infected device. Now, once it finds some, it starts the SSH brute force, what you've seen before, so the 169 different attempts to log in. I assume the main thing why it actually searches or looks for other devices connecting to is to be stealthy. If you randomly start probing out to other devices, you quite often will run into, this device doesn't exist, the root doesn't exist, whatever, and that's very noisy. That can be detected quickly. If you only do a connection back to a device that already connected to your infected device, it's far more stealthy. It's something that one would expect to happen. Now, once a device is cracked, or the password is guessed correctly, that public key is added, as we have seen before. Also, the APC ID file itself is added to there and then spawned. So now we have a self-propagating botnet. Additionally to this, the password is set. Now, this is pretty cool, and this is exactly the reason why I blurred the password beginning, because this adversary decided that on all of the nodes that it was using, it's not only setting that public key, but it's also setting the password to a new password. Now, that by itself is nice and great, but how does the attacker, sometimes we have to look into jump into the position of the attacker. How does the attacker know which bots this network has? Well, for this, the adversary is using dead drops. These are 6 systems, mostly Oracle systems, that were also infected by the adversary at some point. And every time my original infected device jumped to another system and infected a new system, a log line, and then fully encrypted log line is written to these devices. Now, the encryption itself is properly done. I don't know what's in the log line. The transfer process is a little bit different. Turns out that the private key, so the key to actually log into these dead drops, is hard-coded into the APC ID. And it's actually not only hard-coded, it's the root account of the dead drops. So it turns out I have now root access to the dead drops, as well as I know the password that's being set on every single device, meaning I have access to that. Now, to confirm the password theory, you might remember that I said I had to do a lot of debugging to get access to the original Pi. Well, in the first emails back and forth, the user said that they forgot the password because they weren't able to log in anymore. Well, now knowing this, it's pretty clear what happened. Originally back then, I asked them to take the SD card out, overwrite the shadow file with a new hash that I can log in. But before that, asked them to take a snapshot or like a copy, a backup of the original shadow file. Now that's the original shadow file. If you take this, and you can see that 2 users are set. It's the root user and the Pi user. Now, looking at those, and running the command in Linux to create these hashes, these are exactly the same hashes. So yes, I can confirm the adversary is not only setting the public key there, but also changing the passwords to one default password. And it's always the same, which obviously isn't great. Now, that's a lot of effort. Why do that effort? Now, that question is usually a little bit harder in the whole incident response phase. So we dug a little bit further, and we found this. Files or folders that are starting with a dot in Linux are hidden. Now this is the this is the home directory of the Pi user. In this home directory, there are usually no hidden files, or not many hidden files, maybe the bash history itself, but not a folder. There are many. If you go into those, you can see another file. The file is called SSHD. Now for everybody who has maintained a Linux system, SSHD doesn't reside in a hidden folder in the home directory. So taking this file, again, doing the standard magic of incident response, taking the hash and dumping it into VirusTotal, you see, oh yes, this is definitely malicious. 36 different vendors found this as being malicious. Now, if we look a little bit further, and it's hard to see here, you can see that this is a miner. So either the adversary itself or somebody else hijacking the network of the adversary is deploying these coin miners to all of these different systems. Now, why am I not sure it's the same adversary? Well, it also happened on the 17th of December, but about 2.5 hours later. Now, yes, we can trace the login and from where the login comes from, but it also comes from the Tor network. Now, the Tor network obviously hides you, so anybody could be doing this. It could be the adversary, it could be a different group. But that's my guess of why people do this. Now, let's summarize this. Originally, we had 230 systems that my sensor network found. Well, you remember the dead drops? Poking around a little bit on those, it turns out this botnet was 8,654 different networks, different devices. So definitely significantly larger than I thought before. All of these were reporting to these 6 dead drop servers. And well, as stated before, I had full root access to all of the systems because they had hard-coded credentials. So I have full control of this botnet. Now, what do we learn from this? Well, no matter if you're the sysadmin or the most feisty and evil and crazy adversary out there, just don't hardcode credentials, please. We've seen this in a lot of talks over the conference here, from the voting machines to web shops. The second you start using hard-coding credentials, no matter if they are public and private keys or just credentials, it will go south eventually. In this case, south for this botnet. Now, cool that we have access to it, and this was great fun. I really enjoyed, looking at this. But how do we then stop the adversary? Well, obviously I had root access to it, but you can't really log into somebody else's devices, especially because these devices are home devices. These are home routers. This is you going into the home of other people if you log into these devices. So we had to look at something a little bit more sophisticated. The easiest thing you can do is block the attacker. Block these IPs. Fail to ban is the best example here. A lot of systems have failed to ban that if somebody tried to log in multiple times with faulty credentials, you just ban the IP, and this user can't log in anymore. Great, but it's actually not in the community sense. This protects your individual one server, but let's assume somebody else doesn't have failed to ban. Then they will eventually be caught, they will eventually be compromised. So that was definitely not something I wanted to do. I wanted to give something back to the community here by really making sure that this information is also shared with somebody else. Then there's the second option, report to law enforcement. That's exactly what we did with the botnet. Now, there was a lot of bad things said about BKA and the law enforcement here. I actually had really good experience with them. The problem here is these are not a few servers. These are 8,600 home devices. Now, I'm sure you're all the IT people around here, but let's assume your ISP sends you, or the BKA or the police sends you a notification of saying a device in your home is compromised. Or maybe not to you, sends it to your grandma. They're completely lost. So working with law enforcement, especially at this scale, is kind of tough to do that. Also, it doesn't scale. You go to them, you send them an email, and it takes forever to get information back. You go and jump into a call and so on. You can't do this on scale. So I need to figure out something else to do this on scale. And that's getting the ISP involved. ISP, internet service provider, the people that provide you the internet. Well, the cool thing is they can also shut you off the internet if you're doing something abusive there. They also have some sort of system that works to really get the stuff reported and actioned on. Now, I never thought that this worked. But I said, give it a shot. I can't complain about a system not working if I haven't tried it. So went to your favorite LLM of choice and asked them, please write me an abuse email that I can send to an ISP. Did that, and then waited. And then something happened that I never thought would happen. I get an answer. The ISP actually answers me. And actually not only answers me, it's like, thank you for your notification. This is cool. We have seen this before. Can you give us more information? That really sparked the hope in me that this can work. I can really work together with ISPs here to take down malicious setups and systems. Now, sending emails, especially at 12.5 million a day, yeah, maybe not. So I need to find a system that works a little bit better. What we came up with is this. This part you already know. Attack pods, 250 of them, deployed across the internet, dumping everything into a collector, into a pretty big database. Now from there, we combine all of these attacks together that have the same IP. Because there's no point sending abuse notification about an IP multiple times on every single abuse. Next, we scour the internet for the contact of the ISP. Well, first we need to figure out who the ISP is, and then we find the contact. That actually is much easier than thought, but it's, you can absolutely do it. Once we have the contact, we send the contact an abuse notification. And then we monitor the cooldown. Now, what do I mean by monitor cooldown? Obviously, with 250 sensors, it's likely that the abuse IP doesn't only hit one sensor, but actually multiple sensors. So I can see, does the abuse eventually turn off? Does it stop? Not only with my sensors, I can also use other systems. Abuse IP DB is one of the big systems out there where a lot of people are reporting abuses to that system. And using the API, I can figure out if somebody else is seeing that IP abusing. Now, if I see further abuses, there's definitely a follow-up on saying, hey, people, do something. Now, sometimes the ISP doesn't really know what we want to do. Maybe they need some more information, some more up-to-date information, I don't know, something else. I ended up having quite a few emails coming back and something that I can't handle myself. So we monitor for email response coming back, and then we dump that response into an LM of choice. And not only that, we also add all the information that we know about the case to it. And with a bit of prompt engineering here and there, and OpenLlama 3 running beautifully on my home setup, it firstly decides, does the ISP actually need an answer back? Quite often it's like, hey, thank you, or this is your case number or something where we don't need to send an answer back. Now, if we need an answer back, it also decides which answer should be sent back. Now, yes, there is a bit of a check in between, so I don't just by default shoot out emails on the internet, but that way it really scales to really make sure that I can answer these questions in a really short amount of time. Now, once we stop seeing abuses, we close the case. Now, all of you really like efficiency, I guess, because that's why we are IT nerds. We're lazy. We want to do stuff easy, efficient, and so on. This whole setup has a big flaw. And the big flaw is not the computer or the LM. No, it's the human in the loop. I am sending that to a mailbox of the ISP, and the mailbox is a human that needs to read it. Now, if I send thousands of emails, this will not scale. Luckily enough, other much cleverer people than myself have figured out a solution to this. And this is XARF. XARF is an extended abuse reporting format. I'm not sure if you've heard of it, but it's basically a format where you extend the email stack to also be able to send computer-readable information into it in a default format that everybody can build a parser for it. So what you do first is you set a specific content type, making sure it's multi-part report as well as feedback report. That's important because that way they know that's an XARF coming in. Then you add a human-readable part. That's important because obviously not every ISP supports XARF. So you still need some part in the email that is rendered in an Outlook for a human to look at in case the ISP doesn't support it. And after this, you also add the machine-readable part, including the attachments. And that attachment itself includes all the information needed to actually handle the abuse. So in this case, it tells you all the information about the reporter. It tells you that, yes, it's this disclosure, you want to really disclose it. It's the, you want SSH brute force activity, and you also add some logs at the end. Now, using this, the ISP can fully automate a pipeline on their side to check, for example, have there been these ports opened or connections on these ports from these systems being set up to the victim system that I also report here to fully automate that abuse pipeline and eventually take action on it. Now, that's a neat way to automate it, but does it work? I guess. So let's look at some statistics. This setup has been running for about a year now. We have 264,000 abuse cases being set up in the system. We send about 237,000 abused mails. Now, you see the delta there. That's for the ISPs where I was not able to find a contact, and there is no way to reach them. The average takedown time of these abusive mails that we can measure, or abusive IPs, is 5 days. So within 5 days of the IPs that we ever got taken down, we can get them. Now, does it even make an impact? Well, to measure this, let's look at the most abusive IPs that I pulled this morning for the last 30 days. And not only IPs, but I actually clustered them to ISPs, so to ASN numbers in there. And the first ASN is 4134, with, I don't know, too many digits, multiple million of attacks against my network. Now, if you look this one up, this is China Telecom. The big red bubble? Well, likely. Now, the problem with China Telecom is they have on their website an abuse email and everything there. If you send them a notification, it never arrives. It basically says the mail server doesn't exist anymore. Now, it's better than before. I have to admit, before this email, there actually was an email coming back that their mailbox is full. So I thought that was also really funny. But hey, now they decided to just completely kill the mail server. Much, much easier. No more worries. Now, the second one. The second ISP, 14061, is DigitalOcean. Now, with DigitalOcean, I thought, you might be able to work with them, right? Well, it turns out if you send them abuse notification, they support XARF. They support the fully automatic workflow of doing that. And within 28 hours, these systems are reliably taken down. And that's super cool, because these are millions and millions of attacks of thousands of systems that are hosted in DigitalOcean that you can take down within 28 hours, reliable, on average 28 hours reliable, to make sure they don't hit other systems. Now, the third one there, because I wanted to look at the top three, Tencent. Yeah, maybe not as good as DigitalOcean. In here, very similar. You get an email back, better than DigitalOcean, you know, they still have a mail server. But if you read through the email, it basically says, well, we don't handle abuses. We don't care. They do care about government and they do care about copyright abuses, which is great, but if their system tries to attack other systems, they just don't care about it. So yeah. So what's the resume? Can we get abusive systems taken down? And you know, with a year of looking at this and spending quite a lot of time, I would say mostly. As long as ISPs play nicely, and to be honest, most ISPs really do. I had a lot of really cool interactions with different ISPs. I'm cooperating with some German ISPs where I basically sent them the abuse notification. They immediately take down the systems because they trust the data in that network enough. You can really make an impact and make it much, much harder for adversaries to get a foothold at the beginning and then to spray everybody else. So what's next? There are three things. Firstly, use the data. Everything that we do is on our NetWatch GitHub account. So NetWatch is sort of the code name for the whole project. And we, in real time, stream all the abuses that we see to all the standard forums like VirusTotal, Abuse IPDB, and so on, and upload a daily summary of everything to our GitHub account. Now, if you want to do some more research, because you remember 530 clusters, I actually only looked at about 30 of those. So there are 500 clusters out there that still need to be looked into. If you want to do the research, hit us up at data@netwatch.team, and I'm super happy to work together with you, share the data, and actually figure out what you can do with it. Secondly, join the community. Now, this setup works better the bigger our network is. Now, we have all the sensors that we deploy at the moment are from teams and friends and our own sensors. But 250 is nothing compared to everything else out there. Now, if you have a system on your on the internet, maybe a Linux system, but Windows works as well, go to community.netwatch.team, type in your email there. We will reach out to you, give you an API key, as well as instruction how to deploy your own attack pod. With that attack pod, it automatically streams all the attacks that you see into our system, allowing us to have better visibility of what's happening on the internet, as well as to take these systems down and really do something about it. And then finally, this project got much bigger than I thought. So if you want to join in, if you want to have fun taking down, if you want to go down the rabbit hole of looking at these adversaries, take down botnets of thousands and thousands of systems, then reach out at contact, and I'm super happy to work together to actually make this happen. And with this, thank you so much for listening.
Thank you, Lars, for your so important work and this even more important call to action. Yeah, give it again a round of applause for Lars and this project. And I too want to thank and also say sorry that I didn't mention that this talk was also translated into Polish, so thanks also to the person that translated this talk to Polish.
Again, big applause for our translators at C3 Lingo. Thank you.
And all angels.
And now, finally, we come to our Q&A session. We have a few more minutes left. So if you want to address a question to our speaker Lars, come to the microphone. And I think we also have questions from the internet.
Yeah, let's start with the internet. There is one.
There's two actually, but I start with the first one. Did you try any more advanced features for fingerprinting with information that the client might give away while connecting? For example, SSH version and stuff like this?
Absolutely. So, the detail that I showed was just collecting username, password, and IP. That was sort of the first attempt. And I didn't want to go too deep because I only had an hour here. But I'm collecting far more than that. What is actually really, the SSH version works really well as well. What works even better is actually the timing. Looking between two different attacks is very specific timing from one group to another, where you can figure out, do they do a slow scan, a really quick scan, and so on. And combining that with username and password is a really good way to map it.
Thank you very much. There is another question from microphone 2. You moved up quite quickly.
Well, thank you for the talk. Did any of the ISPs you reach out to take interest in your work and maybe want to join NetWatch?
Actually, yes. So we're working with a really big one in the US at the moment, where every IP that is floating, so it's actually not put onto a system like a EC2 instance, that IP gets routed automatically to one of the sensors. So that immediately increases the scale massively eventually. But working with them is kind of hard, but we'll get there.
Thank you. Microphone 1, please.
I have a question more about the scanning infrastructure that you use. So is there a correlation between like wherever you have those scanners running on, like on the cloud provider, versus the botnets that you detected? Like, are they sort of related, that you got like a lot of scans from certain cloud providers or from like, certain sources?
So from the cloud providers, obviously we have seen, there are some cloud providers out there that are more or easier to use by an adversary to spin up instances and run stuff there. What we do see is some geodata of who is attacking who, which is kind of interesting, like from China attacking Europe and US and so on. The problem there is I didn't want to show the data because I don't have enough sensors to actually really make sure it's valid here, and I don't want to do some faulty claims out there. So yeah, that's definitely visible.
Okay. Thank you.
And we have time for a few more questions. Is there another question from the internet?
Yes. Do you know what happens once the ISP receives your abuse report? Does he simply put the IP offline, or does he notify the client, or does it depend on the ISP? Exactly,
it depends on the ISP. So if the ISP is like a good ISP from your home net or residential one, they usually send out a letter or a notification via email to the owner of the internet connection telling them you have a device at home that's actually infected. And working with telecom is really great in that way because they do that really reliable. If the ISP itself is hosting a setup, like in an instance, a VPC, they quite often take these VPCs offline, not by shutting them down, but just disconnecting the network card itself and notifying the user via the interface. Now, the problem with this is obviously downtime for the ISP, so there is a quite substantial amount of verification before that to make sure that it's actually legit.
Thank you. Then microphone 3, please.
Did you saw any lowering of the attacks in your data since you reported the IPs?
We did see some significant lowering from the point that the ISPs were working with us in that, but overall I see an increase in attacks because the number of sensors grew over time. I didn't actually have 250 sensors at the beginning of the year. It grew over time, so we see more and more every single day. And the more community sensors we get, please, the more data we will see.
Thanks.
There is another question from microphone number 6.
Yeah. Did you look into how widely adopted the email extension standard is with ISPs?
Well, we send every single abuse notification with that extended abuse format, and we can see once, depending on the replies we get back from them, and on the other time, the speed that the stuff gets taken down, if they use it or not. We can't 100% confirm it, but we're working with the bigger ISPs one by one to sort of build a relationship to actually get the stuff quicker and faster implemented.
Thank you. So maybe microphone 3 again, please.
Okay, thank you for your talk. I was wondering, with your XR format you're sending there, do you fear abuse of this kind of automated takedown by the ISPs if more players join that game and send automated takedown requests to ISPs?
100%, and that's exactly why we build up this relationship. That you can use it to really abuse it and then send notifications out to the ISP saying, please take this down, while it's actually legit. And so the ISPs will need to check it on their side as well. They don't automatically take it down. But once we build a relationship with them, they trust us and they know that if it comes from this definitive source, they are pretty certain that they can actually take it down.
There is another final question from microphone number 4. You are standing quite long.
Yes, thanks. My question is, I have an IP firewall. It can subscribe to abusive list and then just block it right away. Is there any way, directly or indirectly, to subscribe to such a list?
Form a firewall. Well, there are multiple ones. You know, IOC feeds. They're mostly called IOC feeds. Abuse IPTV. You can pull down all the abusive IPs they get, and there are all sorts of other ones out there. We don't have a feed yet. Mostly because we are not 100% sure on how would we provide it on scale if people subscribe to it. But if that's something that you guys want, that's something that the community says, yes, I want to subscribe to this feed, send us a notification. I'm sure we can build a feed that you can implement in your firewalls and other stuff out there.
Thanks a lot. So I think we've come to an end of this Q&A, but I mean, you have the whole contact details. I think it's pretty clear to join and get into action. And maybe you're also available for
100%.
questions.
So I'm around, I will be around here. Just, contact me and I'm sure you will find me somewhere. Otherwise, just send me an email and we'll chat.
So,
Big applause, make some noise for Lars
Lars.
König. Thank you very much.